Hey everyone, and welcome to this explainer. Today, we're diving headfirst into something totally fascinating, the architecture of digital trust. We're going to trace the entire evolution of how we actually secure our information online. We'll start with the bare bones basics of data encryption and work our way up to the incredibly complex, decentralized architecture of modern blockchains. It's honestly a brilliant progression of mathematical problem solving, and I am so excited to walk you through the whole shebang. Let's get into it. So let's kick things off by looking at the absolute fundamental problem of digital communication. Picture this. You're standing in a massive, incredibly crowded room, and you need to pass a highly sensitive secret to someone all the way on the other side. The catch? Every single person in that room can hear what you say or see what you pass along. Well, that crowded room is literally the public internet. The big question is, how do you keep your message safe while you're transmitting it?
All right, Section 1, the basics of encryption.
At its core, encryption is basically just the process of converting readable data, which we call plain text, into an unintelligible, scrambled mess known as ciphertext. Its one and only job is to protect your sensitive info from eavesdropping or tampering while it's being transmitted or stored. So if someone happens to intercept your message in our proverbial crowded room, all they're going to see is complete gibberish. Now, a great way to understand this is through symmetric encryption, using something like the Advanced Encryption Standard, or AES. In this setup, both the sender and the receiver have the exact same secret key. The sender uses their key to lock the plain text into ciphertext, fires it across the network, and the receiver uses that identical key to unlock it on the other end. It's super fast, and it's incredibly efficient for handling massive amounts of data. But there is a pretty glaring vulnerability with symmetric systems. We call it the symmetrical flaw. Think about it. If you and I have never met, how on earth do I get that shared secret key to you in the first place? If I have to toss the key to you across that same insecure crowded room, an interceptor can just snatch it out of the air. And if they have the key, well, they can read absolutely everything. Moving right along to Section 2, solving the key exchange. So the real game changer here is asymmetric encryption, which is also known as public key cryptography. While our symmetric encryption uses one shared key and runs super fast, asymmetric encryption uses a mathematically linked pair of keys, a public key and a private key. This totally solves the sharing problem. The trade-off, though, is that it requires much longer keys and is definitely a lot heavier computationally. Let's think about the asymmetric process in action, something like the RSA system. Basically, you generate a key pair, and you publish your public key to the whole world. Anyone, and I mean literally anyone, can use your public key to lock a virtual box with a message inside. But because of the math involved, that public key cannot unlock the box. The only thing in the universe that can decrypt that ciphertext is your secretly held private key. Since you never actually share your private key, you completely eliminate the risk of interception. Pretty brilliant, right? But remember how we just said asymmetric encryption is a heavy lift computationally? Yeah, we really don't want to use it for everything. Enter the Diffie-Hellman key exchange. This is a clever workaround where two parties, let's go with the classic Alice and Bob, can build a symmetric shared secret over an insecure channel without ever transmitting the final key itself. They just agree on some public parameters, mix in their own secret numbers, swap the resulting public values, and then they both independently calculate the exact same shared secret key. Let's break down the actual math for a second, just to see how elegant this is. Alice and Bob agree on a prime number, let's say 23, and a primitive root, 5. These are totally public. Now Alice secretly picks the number 6, and Bob secretly picks 15. They do a bit of modular arithmetic and swap their public results, 8 and 19. Then they run the calculation one more time with their secret numbers. Thanks to the magic of discrete logarithms, they both arrive at the exact same secret key, k equals 2. An eavesdropper sees the 23, the 5, the 8, and the 19 floating around the room, but it is mathematically unfeasible for them to reverse engineer that secret key 2 from those public numbers. And hey, this isn't just some theoretical textbook math. This exact Diffie-Hellman setup powers Transport Layer Security, or TLS. That's the protocol securing the connection between your web browser and whatever server you're pinging right now. Your browser and the server use certificates to authenticate who they are, and then they seamlessly negotiate a symmetric session key using Diffie-Hellman to encrypt your entire web session. Which brings us to Section 3, Public Key Infrastructure. Okay, so we've solved the key sharing problem. Awesome. But that actually introduces our next major hurdle. The thing is, great math doesn't verify identity. A hacker could easily intercept your connection, pretend to be your bank,
and just send you their own public key. You'd set up a perfectly secure, encrypted tunnel straight to the hacker. No good. We desperately need a way to prove that a public key actually belongs to the person or the organization it claims to. And that is exactly where Public Key Infrastructure, or PKI, comes to the rescue. PKI is a framework that relies on central certificate authorities. You can think of these authorities as the trusted bouncers of the internet. Their job is to verify an organization's identity and then digitally sign a certificate that binds that identity to a specific public key. So when your browser sees the bouncer's signature, it knows it can trust the key.
But as our source material makes very clear, there's a catch. Centralized authorities create a single point of failure. This is the big structural weakness of PKI. We're relying entirely on a centralized hierarchical authority. If that certificate authority gets compromised, issues a bad certificate, or simply goes offline, trust in the entire system can collapse in the blink of an eye. That leads us perfectly into Section 4. Enter the blockchain. So blockchain is a type of distributed ledger technology, or DLT, and it fundamentally shifts the entire paradigm. Instead of relying on a central database held by one authority, a DLT is a globally distributed database. Every single node, meaning every participant in the network, holds a complete, updated copy of the ledger. This total decentralization completely wipes out that single point of failure we just saw in PKI. If one node goes down, the network doesn't even blink. It just keeps operating. And the way cryptographic hashing achieves this security is just so cool. It basically takes everything we've talked about so far and uses it to tightly chain data blocks together. Each block contains a header with the cryptographic hash of the block right before it. If a malicious actor tries to sneak in and alter a transaction in a past block, the hash changes immediately. That breaks the link to the next block and every single block after it. It makes the historical record mathematically tamper-resistant and totally unalterable. And finally, Section 5, Decentralized Consensus Mechanisms. Now, this introduces the final piece of our puzzle. If there's no central boss running things, and everyone has their own copy of the ledger, how does the network actually agree on what's true? Like, which transactions actually get added to the next block? Well, that is handled by consensus mechanisms. Since there's no central gatekeeper, the network relies on protocols like proof of work, where miners solve incredibly complex cryptographic challenges, or proof of stake. These mechanisms allow the distributed network to democratically validate new transactions and agree on the current state of the ledger. Think about how participants and delegates interact in this decentralized decision-making flow. A leader proposes an optimal solution, like, say, a newly mined block, and sends it out to the followers. The followers then independently verify the validity of those transactions. If everyone agrees the math checks out, it's accepted. But if the leader tries to pull a fast one and be dishonest, they're immediately removed. This distributed consensus elegantly prevents tampering in issues like double spending, all strictly through network-wide agreement. From securing a single key with math to securing massive global networks with distributed ledgers, the evolution of digital trust is just absolutely incredible. But as we look to the future, especially with the impending rise of post-quantum cryptography and AI, we really have to ask ourselves, will our current cryptographic chains actually hold, or are we on the verge of needing a completely new set of building blocks? It's a fascinating question and one we are definitely going to be exploring more in the future. Thanks so much for joining me on this explainer, and keep learning.